Now that we've talked a lot about solids and liquids, we can talk about phase diagrams. Phase diagrams depict the relationship of pressure and temperature to the gas, liquid, and solid states of a given compound. And in general, they have pressure on the y-axis and temperature on the x-axis. So we can see how pressure varies as a function of temperature and how that affects the phase of whatever compound you're talking about. So here I've drawn this kind of fork, and lots of phase diagrams all look kind of different, but this is like a basic phase diagram. Um, the tines of the fork in the phase diagrams, so kind of here and here, these kind of areas of it, these demarcations, separate the phases of matter of whatever compound you're talking about, you're describing with the phase diagrams. So I hope it makes sense to everybody that at high pressures and low temperatures, your substance would be most apt to be a solid. Okay, high pressure, very dense. Okay, that would be the solid structure. At high temperatures and lower pressures, you're more likely to have the gas or the vapor phase. So I hope that makes sense to everybody intuitively that at higher temperatures and lower pressures, you would have the gas or the vapor phase. In the middle, you have the liquid phase. Now, anywhere along the line, you are in equilibrium with the two phases. So anywhere along this line here, I would be in equilibrium between the liquid phase and the gas phase. Anywhere along this line here, I would be in equilibrium between the solid and the liquid phases of whatever the compound is that I'm talking about. And then anywhere along this line here, I would be in equilibrium between the solid and the gas phases. So that's of course is corresponding to sublimation. Okay, so along this purple line here, that is where I have sublimation. Okay, the equilibrium between solid and gas. Along the green line, I have vaporization, or the opposite, condensation, the equilibrium between the liquid and the solid. And then along the red line, I have uh, vaporization or condensation, the equilibrium between the liquid and the gas. Uh, Liquid and solid is not condensation. Liquid to solid is obviously freezing. Okay, so these lines here demarcate the phase transitions between the solid, liquid, and gas phases. Now, there are a number of things that you can kind of get out of a phase diagram. Let's just arbitrarily say that on my pressure axis here, the pressure is 1 atmosphere right here. That means as I go across that I have the normal boiling point here. Okay, so my normal boiling point would be the temperature where I have the phase transition between liquid and gas at 1 atmosphere. I would also at 1 atmosphere have the normal melting point. Okay, the normal melting point where I have the equilibrium between the liquid and the solid. What else can you extract from this phase diagram? Oh, very important thing is the triple point. So this little T here marks what's called the triple point. So the triple point is where kind of all those demarcations come together in the phase diagram. The triple point is a special point where all three phases exist in equilibrium. The solid, liquid, and the gas are all in equilibrium at that triple point. Very unique point. What else do we have? The critical point. Okay, so the critical point here, demarcated with this C here, corresponds to a critical temperature and a critical pressure. So let me get a different color. Kind of go down here to show. Oops, don't want that. That is too thick. Let's see, I'll just kind of sketch it like this. All right, still too thick, but that's okay. So here on the y-axis, we have pressure. So this is the critical pressure. And here on the x-axis, we have the temperature. So that's going to be the critical temperature. So this critical point gives us these two quantities, the critical temperature and the critical pressure. So the critical temperature, this is the critical temperature. Above that temperature, the substance cannot be a liquid at any pressure. And that's because we essentially have it going like this up to infinity there. That means that that is the temperature barrier. Above that, you have a gas. The substance cannot exist as a liquid no matter how much pressure you put on it. Okay, it's always going to be a gas. So that's what the critical temperature means. On the y-axis, you have the critical pressure denoted by the critical point. The critical pressure is the pressure that has to be applied to a substance at the critical temperature in order to just maintain the equilibrium between liquid and vapor. Okay. So critical temperatures are kind of interesting because they kind of tell you, in the way that a boiling point tells you a little bit about a different substance, critical temperatures give you a little bit of information about a substance. So let's compare carbon dioxide and water. Critical temperature and the critical pressure for each of those substances. So for carbon dioxide, the critical temperature is 31 degrees Celsius. Okay, remember, the critical temperature is the temperature above which the substance can't be a liquid at any pressure. So that means that any temperature above 31, you can only have carbon dioxide as a gas. Okay, you cannot liquefy it, no matter what pressure you apply. For water, as you might guess, the critical temperature is much higher. Okay, and that is from all of those hydrogen bonds, right? So the critical temperature is 374 degrees Celsius for water. So that's more than 3 orders. That's more than 10 times. That's more than 10 times the critical temperature of carbon dioxide. What that means is that above 374, you cannot liquefy water. Okay, it's going to be water vapor only, no matter what pressure you apply. And the corresponding critical pressures are 73 atmospheres for carbon dioxide and 218 atmospheres. And once again, the critical pressure is the pressure that has to be applied at the critical temperature to maintain the liquid vapor equilibrium, kind of along that line in the phase diagram. Okay, kind of going all the way up here. So I hope that makes sense, and you should be able to kind of extract this sort of information when you see a phase diagram.